Oh, okay, so you should be done with Simon 7.7. Fairly straightforward. Plug in, get the force between two objects. And so, not incredibly profound. You're like, okay, well, I now know the force between two objects in space. That might seem handy, but not really great. But there are some profound things that come from this. One of the first things that are profound is I can tell you what the acceleration of gravity is on almost any planet. But exactly, I can tell you the force of gravity on almost any planet. Well, how can that be? Well, one of the first things we could do is if I have the following information. So the starting point of this idea is the acceleration of gravity is found by dropping stuff and seeing how fast it falls. It's the acceleration, right, we get, which means F net is the sum of all forces, and the force of gravity is the force we're talking about, agreed? On the left-hand side is our mass times acceleration. And in this case, it's G, right? So it's our mass times acceleration of gravity. Force of gravity is G m1 m2 over r squared. Now we look back at this formula, we say, well, wait a second. I've got a mass on both sides, but which one cancels out? Well, if we're talking about acceleration to gravity, well, then the object you're dropping doesn't matter, right? That's what we're weighing on the left. And that's what's equal to the force of gravity on the right. So that's the same force on both sides. The second mass, this is going to be the mass of the planet. Although it could be an asteroid or something else you want to find the acceleration of gravity on. What's the r? The r is the radius of the planet. Now, initially you might be thinking, but Mr. Resny, I can't find the mass of a planet. Well, we'll talk about how you can find the mass of a planet. It's actually not that hard for most planets, okay? So what you're going to do when you want to find the acceleration of gravity to some places, you're going to set force of weight equal to force of gravity. You're going to note that's mg is equal to g m1 m2 all over r squared, and then the m's are going to cancel out, and that's how you find your g. So for example, let's do the example problem, sample problem number 3. Sample problem number 3, a moon. The moon has a mass of 7.36 times 10 to the 22nd kilograms, with a radius of 1.74 times 10 to the 6 meters. What would be the acceleration of gravity of a 1 kilogram object there? So I'm going to go force of weight has to be equal to force of gravity on the moon. No, you're not weightless on the moon. You do have weight. You just don't have very much. Okay, so we would say mg is equal to g m1 m2 over d squared, over r squared, sorry. Used to be d in my old formulas. Okay, so m's, so this is the mass of the object I'm dropping, the mass I'm weighing. I don't know what g is on the moon, so I leave that off. This g is the 6.67 we were dealing with earlier, 6.767 times 10 to the negative 11th. The mass of the first object's 1. The mass of the moon is 7.36 times 10 to the 22nd. All divided by 1. The radius of the moon, 1.74 times 10 to the 6th squared. Put this all in my calculator. Now, before I move much further on, note this 1 here is going to cancel out every time, which makes sense because we know acceleration of gravity does not depend on the thing you're dropping, right? It can't, right? So that's the thing that's never going to matter. But you can write it down every time if you like, and cancel it out if you like. You're totally allowed to do that. 7.36 exponent 22 divided by 1.74 exponent 6 squared. Oops, that's 6 squared, delete. Took that in wrong. And I get the acceleration of gravity on the moon. Acceleration of gravity on the moon is 1.62 meters per second squared. And by the way, that is the acceleration due to gravity on the moon. Okay, this, by the way, was calculated before anybody ever stepped on the moon, anybody weighed anything on the moon, anybody dropped anything on the moon. Okay, the only caveat was we had to orbit something, so we'll have to talk about that when we get to orbiting, but not right now. So this is how you can find the acceleration of gravity anywhere. So on the asteroid Ceres, which has a mass of 1.17 times 10 to the first kilograms and a radius of 3.8 times 10 to the fifth, what would be acceleration of gravity of the moon? So you go to one of these asteroids, you go stand on it. What would be the acceleration of gravity? Would we expect it to be much? Probably not. Okay, so mg equals gm1 m2 over r squared. The m's cancel out. G is equal to, I don't know, but I got 6.67 times 10 to the negative 11th. Sorry about my bad 6.7 there. Mass of Ceres is 1.17 times 10 to the 21st, all divided by the radius squared, which is 3.8 times 10 to the fifth squared. So I get out my handy dandy calculator. I go 6.67 exponent negative 11th times 1.17 exponent 21st divided by 3.8 exponent 5 squared, and I get the acceleration of gravity on Ceres, one of the biggest asteroids there are, would be a whopping 0.540 meters per second squared. To give you a feel for how weird that would be, if you were to fall off a 10-story building, 10-story building would be about 30 meters. Let's calculate how long it would take you to hit the ground. 0.540 t squared. So 30 squared. No, what am I doing? Not 30 squared, sorry. 30 times 2 divided by 0.54 square root. It would take you 10 full seconds to hit the ground. 10 full seconds to hit the ground. 10.5 seconds to hit the ground. Okay, on planet Earth, that would take you, let's do a quick calculation, times 2 divided by 9.8 to the 0.5. It would only take you 2.5 seconds to hit the ground. So it would be a lot longer. Dropping something from 1 meter on Ceres would be negative 1 equals 1/2. 0.540 t squared would take 2. Take 2 full seconds to the ground. 1 meter above the ground, take 2 seconds to hit the ground. You go 1 Mississippi, 2 Mississippi before it hits the ground. 1 meter above the ground. Okay, so you now have the ability to do 7/8. Go ahead and do 7/8, and hopefully next time we'll actually have a class, and we'll see what we can talk about before this is over. Bye.